Hi, good morning. In this recording, I will go over magnetic field and magnetic forces. We will here be able to talk about the properties of magnets and how they interact with each other. We will also be able to analyze magnetic forces on charges which are moving, and also current carrying conductors. We will also go over some of the applications and also study something about how current loops behave when placed. And this is like the interaction between electricity and magnetism when placed in a magnetic field. Okay, the first thing we are going to talk about is magnetic properties, and the first thing is magnetic poles. We know that like for every magnet, okay, and maybe like this is something that like from early school you have access to these type of bar magnets where we can say this is a south pole and this one is the North Pole. Now, this is really here something that we, like for every magnet, we are going to have a South Pole and a North Pole, even if you cut it into smaller pieces, let's say in half first, then you're gonna get two magnets again, south north, and cut more. You will even like the smallest magnet is gonna have the south and the north. Now, one also important rule, it is opposite poles attract each other, and like poles repel each other. All right, then here if you have the two magnets, this is the north, this is the south, this is the north, this is the south, they're gonna repel each other, then the force is gonna be away from each other. If you have them like you have for this one you have the north here and the south here, and for this one you have the south here, north here, then you are going to have these are really, they are going to attract each other. Now, also, we need to know that magnetic poles always come in pairs. We cannot separate them, okay? Then we don't have what is called magnetic mono. Mono means one. Monopoles do not exist. All right, now I will say here, of course, because of the, because of the magnetism, we're gonna feel these forces. We call them magnetic forces. But also, something that we can say is how these magnets, or like how these magnetic fields, how these can be created. One thing that is really very important, that if we have a moving charge, and of course moving charge means a current, it creates a magnetic field. Now, also here we will use for magnetic fields B. This is, we call it magnetic field. And now, like whatever, like, the source of this magnetic field, we want to see that we are going to have let's say a field that might be let's say from west to east. Then I will represent this is like a uniform magnetic field, and it's like the same way that we did represent electric field lines. We can express and find the magnetic field lines. And I think maybe you did the experiment in the lab, or if you did not do it, like you did it maybe in early classes of science, where we can map the magnetic field lines, and they are always like leaving the north and entering the south, and like they have of course, depending on what is really the shape of the magnet, you're gonna find that you will be able to map them. Now, what is really very important here, that I can calculate, if I put a charge in a magnetic field, then I can calculate the magnetic force on a moving charge. And this topic is really important for us. And something here that I want you to know, that the force that we are going to have here can be calculated as F equals Q, which is the charge, V cross B. Now this is the force as this is the force as a vector. Now remember we studied cross product in physics 201, and in this course we said like the magnitude is gonna be Q V B sine theta. Then this is just for the magnitude. You can determine what is really the the magnitude of the force. Here Q, it is the quantity of charge, in coulomb, and V, it is the velocity in meters per second, and B, it is the magnetic field measured in Tesla. This is the unit, this is a new unit. Therefore, here I will say, okay, depending on what is really the angle between V and B, we are going to have the, what's the magnitude. Now, there is a very special case. And that is when a moving charge is moving perpendicular to the magnetic field. Here, what we have, I'm gonna represent B. It is along the x-axis, all right? And I will say V, it is perpendicular to I don't want to, yeah, it's along the Z. I don't want to draw it like this. I'm going to draw it like this, but you know that this is really 90 degrees. Okay, and this is really V, and this is really the charge here, Q. And we will find that the force, okay, always, the force, this is always the direction of the force, is going to be here, perpendicular to the plane. Then F is going to be perpendicular to the plane that contains both B and V. Now, here when I said it's a special case, it's a special case that it is the sine theta is going to be 1. But like the force always, in all the cases, regardless what the angle is going to be, perpendicular to the plane that contains both B and V. Here, this is the special case that I was talking to you. The magnitude is going to be a Q VB sine 90, and that is going to be QVB. All right. Now, we need to know that when V is not perpendicular to B, then here you need to know what is sine theta, and you are going to have it in the equation. Now, how we can determine, now, remember we said this equation here is just for the magnitude. How to determine the direction of the force? We said it is perpendicular to the plane, but we need to know how to determine it. Now, the first thing is we are going to say we have something here called right hand rule. Sometimes we can say it's RHR. All right, that the right hand rule, okay, we are going to apply to find the direction on a positive charge. Then if the charge is negative, we're gonna say reverse, the opposite. But let's say talk now about the applying the rules for a positive charge. First, we're going to place V and B as vectors tail to tail, which means I have, I used red for, let's say, the B, and the blue for you know, the blue for V, and the charge here, it is a positive charge. Now number 2, imagine turning V toward B in the same plane that contains both vectors. All right, then here I'm gonna try to rotate that vector into this direction. Now it comes here, really the right hand rule, curl your right hand, then the fingers of your right hand around this line. The same direction of rotating V, and then your thumb is going to point in the direction of F, the force. Then here, if let's say I'm gonna make my fingers in that, okay, my thumb is gonna be up. Okay, then this is the direction of the force. Okay, I'm gonna curl my fingers in that direction. Now, if the charge is negative, then find the direction for a positive charge, then say for a negative charge it should be in the opposite direction. Also, I want to review here with you when you have, let's say, okay, I can sometimes have V as Vxi plus, like in components, Vy j plus Vzk, and I have the force as, not the force, B, the magnetic field as Bxi plus Byj plus Bzk. Then now, if I want to calculate the force, it's QV cross B. Remember, V cross B is different from B cross V. Okay, and here we can use the determinant, which is here I, J, K, and then here this is gonna be Vx, Vy, Vz, and here Bx, By, Bz. And I can do that, like I always like to maybe, let's have a big bracket here, like for the I component, you're gonna cover the I, and then you're gonna say it is VYBZ minus VZBY. Here I have a negative, and I'm gonna cover the J, and I'm gonna say it is VXBZ minus VZBX. Please review that from your physics 201, plus the last one is gonna be VXBY minus VYBX, and that is K, and this is how we're gonna calculate the vector that represents F. I'm gonna stop here, and then I'm gonna solve one problem related later. Thank you.